Section 14.4, Dependence of Reaction Rate on Temperature. So now we're going to look at the effect of temperature on the speed of a reaction. Nearly all reactions happen faster at higher temperatures. For example, the time required to cook food depends largely on the boiling point of water. Cookbooks sometimes give alternate directions for cooking at high altitudes where the lower atmospheric pressure results in water boiling at a lower temperature. The reaction involved in hard boiling an egg happens faster at 100 degrees C, about 10 minutes, than at 80 degrees C, about 30 minutes. The dependence of reaction rate on temperature is the reason that we keep food in a refrigerator and why food keeps even longer in a freezer. The lower the temperature, the slower the processes that cause food to spoil. Collision theory. Chemical reactions generally occur as a result of collisions between reacting molecules. A greater frequency of collisions usually leads to a higher reaction rate. According to the collision theory of chemical kinetics, the reaction rate is directly proportional to the number of molecular collisions per second. Rate is proportional to the number of collisions per second. Consider the reaction of A molecules with B molecules to form some product. Suppose that each product molecule is formed by the direct combination of an A molecule and a B molecule. If we doubled the concentration of A, then the number of A-B collisions would also double, because there would be twice as many A molecules that could collide with B molecules in any given volume. Consequently, the rate would increase by a factor of 2. Similarly, doubling the concentration of B molecules would increase the rate twofold. Thus, we can express the rate law as rate equals K, the rate constant, times the concentration of A, the first reactant, times the concentration of B, the second reactant. The reaction is first order in both A and B and is second order overall. This view of collision theory is something of a simplification, because not every collision between molecules results in a reaction. A collision that does result in a reaction is called an effective collision. A molecule in motion possesses kinetic energy. The faster it is moving, the greater its kinetic energy. When molecules collide, part of their kinetic energy is converted to vibrational energy. If the initial kinetic energies are large, then the colliding molecules will vibrate so strongly as to break some of the chemical bonds. This bond breaking is the first step toward product formation. If the initial kinetic energies are small, the molecules will merely bounce off of each other intact. There is a minimum amount of energy, the activation energy, E sub A, required to initiate a chemical reaction. Without this minimum amount of energy at impact, a collision will be ineffective. That is, it will not result in a reaction. Student note, kinetic energy is the result of motion of the whole molecule relative to its surroundings. Vibrational energy is the result of motion of the atoms in a molecule relative to each other. When molecules react, as opposed to atoms react, having sufficient energy is not the only requirement for a collision to be effective. Molecules must also be oriented in a way that favors reaction. The reaction between chlorine atoms and nitrosyl chloride, NaCl, illustrates this point. Cl plus NaCl gives you Cl2 plus NO. This reaction is most favorable when a free chlorine atom collides directly with the chlorine atom in the NaCl molecule, figure 14.11a. Otherwise, the reactants simply bounce off each other and no reaction occurs, figure 14.11b. So take a look at these two figures, A and B. Let's look at A first. Before, the chlorine atom, which is green, is colliding with another chlorine atom, boom, collision, and then that's enough energy to break off the nitrogen and oxygen, the blue and the red one. Successful reaction. But if you look at B, if the chlorine atom is moving too slowly, if the chlorine atom is not oriented properly and it collides into the oxygen atom, sure, there could be a collision, boom. But it's not oriented properly to the other chlorine to form a bond with the other chlorine atom. So it'll just bounce off the oxygen atom, and sorry, no reaction took place. Figure 1411. For an effective collision to take place, the free chlorine atom must collide directly with the chlorine atom in NaCl. NOCl. Otherwise, the reactants bounce off one another, and the collision is ineffective. No reaction takes place. When molecules collide in an effective collision, they form an activated complex, also called the transition state, a temporary species formed by the reactant molecules as a result of the collision. 14.12 shows a potential energy profile for the reaction between chlorine and nitrosyl chloride, NaCl. Take a look at that. If you look at this graph, on the y-axis is potential energy, on the x-axis is reaction pathway. The chlorine is colliding with another chlorine, and the one in the NaCl. They're forming what's called an activated complex. This is a combination of the two reactants. The energy is very high at this point. And then what happens is they lower in energy and they break off into products. This is the energy profile for the reaction of Cl with NaCl. In addition to being oriented properly, reactant molecules must possess sufficient energy to overcome the activation energy. We can think of the activation energy as an energy barrier that prevents less energetic molecules from reacting, because the number of reactant molecules in an ordinary reaction is very large. The speeds, and therefore the kinetic energies of the molecules, vary greatly. Normally, only a small fraction of the colliding molecules, the fastest moving ones, have sufficient kinetic energy to exceed the activation energy. These molecules can therefore take part in the reaction. The relationship between rate and temperature should make sense now. According to kinetic molecular theory, the average kinetic energy of a sample of molecules increases as the temperature increases, right? They go faster if it's hotter. Thus, a higher percentage of the molecules in the sample have sufficient kinetic energy to exceed the activation energy, right? So think about it this way, coming back to figure 1412. If those molecules collide with not enough energy, they can't overcome that hill. If they overcome that hill, however, you'll get products. Temperature is what determines how much energy they start with. Figure 14.13. Kinetic molecular theory shows the average speed and therefore average kinetic energy of a collection of molecules increases with increasing temperature. The blue line represents a collection of molecules at lower temperature. The red line represents the collection of molecules at higher temperature. At higher temperatures, the more molecules have sufficient kinetic energy to exceed the activation energy and therefore undergo effective collision. Collision theory gives us a way to visualize how reactant concentration and temperature affect reaction rate. Figures 14.14 and 14.15 illustrate these effects at the molecular level. 14.14. At higher concentration, reactant molecules collide more frequently. They're just closer to each other on average, so they collide more frequently, giving rise to a greater number of collisions overall, which increases the number of effective collisions. An increase in the number of effective collisions increases the reaction rate, right? The more frequently they're colliding, the more often they're going to successfully produce a product. Faster reaction. Figure 14.15. When temperature increases, reactant molecules move faster. This causes more frequent collisions and results in greater energy at impact. Both factors increase the number of effective collisions and cause an increase in reaction rate. So if it's hotter, they move faster. That means they have more energy, more kinetic energy to break the chemical bonds that are required to be broken in order for this reaction to take place. Now we're going to move into mathematics of this. The Iranian equation The dependence of the rate constant on a reaction on temperature can be expressed by the Iranian equation. K equals A times E raised to the negative E sub A divided by RT. That is called equation 14.8. Where E sub A is the activation energy of the reaction in the units of kilojoules per mole. R is the gas constant, 8.314 joules per kmol. And T is the absolute temperature, meaning the Kelvin temperature. E is the base of the natural logarithm. The quantity A represents the collision frequency and is called the frequency factor. It can be treated as a constant for a given reaction over a reasonably wide temperature range, meaning that if you change the temperature by thousands of degrees, or even hundreds, it might change a little bit. But if you keep the temperature the same within a couple hundred degrees, it should be pretty much a constant. This equation equation 14.8 shows that the rate constant decreases with increasing activation energy. So it'll go slower if the activation energy is larger, and increases with increasing temperature, meaning it'll go faster at higher temperature. This equation can be expressed in a more useful form by taking the natural logarithm of both sides. Take the ln, the natural log of both sides. If you do that, ln of k equals ln of ae minus e sub a over rt, you get ln k equals ln a minus e sub a over rt, and that is equation 14.9, which can be rearranged to give the following linear equation. Remember, we saw that in the previous section. By taking the log of both sides, you can turn something into a linear relationship, which you can graph. ln k, which is y, equals minus e sub a over r, which is the slope m, times 1 over t, which is x, plus ln of a. That's equation 14.10. All they've done in 14.10 is just rearranged it. They left the left side the same. They moved the ln a to the back, and they just made it so that the t is written, since it's in the denominator, is written as 1 over t. Okay? Y equals mx plus b. So the reason it's done that way is to make it so that you could graph it. Student note, absolute temperature is expressed in kelvins, section 1.3. Thus, a plot of ln k versus 1 over t gives a straight line whose slope is equal to minus e sub a over r, and whose y-intercept b is equal to ln of a. Sample problem 14.8 demonstrates a graphical method for determining the activation energy of a reaction. There's sample problem 14.8. Practice problem A, practice problem B. We can derive an even more useful form of the Arrhenius equation, starting with equation 14.9, written for two different temperatures, T1 and T2. Now, this is a bit of a editorial issue. It may not be more useful form, but it is a different form. So let's imagine that we're going to do this experiment with two different temperatures, T1 and T2, and measure K, so K1 for T1, and then K2 for T2. We would get that ln of K1 equals ln A minus EA over RT1. So that's the first temperature and the first rate constant. And then ln K2 equals ln A minus EA over RT2. So that's the second temperature, second rate constant. Remember, it's a constant at the same temperature. But if you change the temperature, the rate constant changes. The Arrhenius constant A doesn't change, but the rate constant K does. That's an important factor. Rate constant depends on temperature. So now, suppose we just say, hey, let's just take ln K2 minus ln K, or other way around, ln K1 minus ln K2. That would equal ln A minus EA over RT1 minus ln A minus EA RT2. The ln A's cancel, right? So now you have ln K1 minus ln K2. However, if you have the difference in logs, ln K1 minus ln K2, the difference in logs is equal to the log of the ratio. So that difference can be expressed as ln K1 over K2. That would be equal to minus E sub A over R. We're going to factor out the EA over R, and then we would have minus 1 over T1 plus 1 over T2. Well, if you have minus something plus something else, you write the second term first minus the first. So now you get ln K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. So if you know two temperatures and you know one of the rate constants, you can predict the other rate constant. Student note. Note that for two different temperatures, the only thing in equation 14.9 that changes is K. The other variables A and E sub A, and of course R, are constant. Okay? Equations 14.8 through 14.11 are all Arrhenius equations, but 14.11 is the form you will use more often or most often to solve kinetics problems. Equation 14.11 enables us to do two things. One, if we know the rate constant at two different temperatures, we can calculate the activation energy. Two, if we know the activation energy and the rate constant at one temperature, we can determine the value of the rate constant at any other temperature. Sample problems 14.9 and 14.10 show how to use equation 14.11. Now, I will point out that that statement, that's a claim. Equation 14.11 is the form you will use most often to solve kinetics problems. That may be true in this textbook, but in reality, people are more likely to use the earlier form and do a graphical analysis. So I'm not sure why the author really is promoting this 14.11 over 14.9, but that's her choice. So there's sample problem 14.9, 14.10, and then some checkpoints, and that ends this section.